everyone, welcome back. So in this video, we are going to talk about some of the mathematical tools that you are going to need in this course on fluid mechanics. And so we're going to go over these tools briefly, just so that we're all on the same footing. We understand the terminology and the notation that I plan to use throughout the rest of this course. And it also is a good way for you to check your own understanding and where you're at to see if there's any areas of mathematics that you might need to brush up your skills on. All right, so we are going to be working on mathematical tools for fluids. Again, all of this should be reviewed to you. So if any of it feels a little shaky, please use this time to refresh yourself or reach out for help. So the first thing that we're going to talk about, or I'm going to remind you that we'll need in this class, is derivatives. Of course, that should probably be no surprise to you. All right, and I will remind you that a derivative essentially is going to look like this. So if we have some function f, I'm going to just draw a general function here that depends on a variable x, like this, we can express the slope at any point on this function as the following. So it can be approximated as the value of the function at some location x plus delta x minus the value of the function evaluated at x divided by the difference between x plus delta x and x, which is of course just delta x. All right, so I will draw that here on this plot. So we have, for example, this is x plus delta x. This is x. And then, of course, this is f of x. And this point here is f at x plus delta x. And the distance between these two lines is just delta x. All right, so hopefully this is very familiar to you from Chem 1. And so by taking this approximation of our derivative, we can then say, well, what if we take the limit as delta x goes to 0? And so if you do a little thought experiment here, as you take this position delta x and you shrink it down to 0, these 2 points are lying essentially right on top of each other. And so this approximation becomes very, very good and gives us our derivative of x with respect to x, of f with respect to x. All right, a little note on notation here. This is going to be useful for the rest of the class. So when I write d dx, for example, you'll notice that these letter d's are kind of a traditional print. This represents a total derivative. And what I mean by that is when a derivative is a total derivative, that means, for example, in this df dx, my function f only depends on x. So the derivative is a total derivative. If I wrote d dx like this, with the script d looking d's, this is a partial derivative with respect to x. And what this implies is that if I had an expression partial f, partial x, this means I'm taking a derivative with respect to x, but my function depends on variables in addition to x. Okay? You're also going to be careful with this notation when we start integrating things, because when we have partial derivatives, instead of just having constants of integration, we end up with functions of integration. So this becomes important for integration. And just to give you a quick example, suppose we want to integrate some function which depends on x with respect to x. We will end up with our expression, our integrated version of f of x, so I'm going to call it capital X, and then we end up with a constant of integration. All right, if this function f depended on something more than just x, so if, for example, we are integrating f that's a function of x and y, and when I do this, I will use this notation to avoid confusion. What we end up is, with our integrated function, which is going to be a function of f of x and y, plus we will have a constant function of integration that depends on y. All right? To convince yourself of why this only depends on y, consider that if you integrate this, if you take the derivative of this, you need for this term to go away. All right? The only way it can go away is if it does not depend on x. So this is constant with respect to x. Okay? All right. So this is a little primer on derivatives, just a reminder about kind of where they come from, what they mean, a little discussion about total versus partial derivatives, as well as how to handle constants of integration in the event of integrating something that has partial derivatives. The next thing that we're going to want to talk about is what different types of quantities are in mathematical expressions. All right, so the first one that we all know and love is scalars. All right, and a scalar is just a quantity that is specified by a real number, but it has no direction, okay? So some examples of scalars that we're used to talking about in fluids and just generally in engineering and science are things like volume, temperature, and mass. So for example, temperature. All right, if we take a scalar and we give it a direction, then we have what is known as a vector. So a vector is a quantity specified by a magnitude and a direction. All right, so these are things like velocity, acceleration, force. Okay? Vectors are treated in a little more complicated way than scalars, right? Scalars, we have our normal operations of addition, subtraction, multiplication. I trust that we all feel pretty comfortable with that. Vectors, we need to be a little more careful. There's some more rules to take into account. And so I'm going to go over the more common ones that we're going to see in this class. The first one is the norm or magnitude of a vector. All right, notation-wise, I will generally denote this as 2 lines. The vector is going to have a little arrow over the top, and then another 2 lines. So the arrow over the top denotes a vector. The 2 lines on either side denote that we're taking the magnitude or the norm of that vector. And this is calculated by taking the square root of the sum of the squares of each of its components. All right, so I have the x component squared plus the y component squared plus the z component squared. All right, and the square root of that sum is the magnitude or the norm of that vector. Just for some additional notation, I can call my vector A with a little arrow over it, and I can break that down into kind of a component formulation of this vector as either ax, ay, az, where here I have my vector magnitudes in each of the x, y, and z directions set as a pair like this. Or equivalently, I can write this as the x component in the I hat direction plus the y component in the j hat direction plus the z component in the k hat direction. All right, these are equivalent. This pairing and ordering implies the I hat, j hat, k hat direction. And then just for some additional clarity, if this is our standard coordinate system where we have x, y, and z, this is going to be my I hat, this is my j hat direction, and this is my k hat direction. Also, keep note that I hat, j hat, and k hat are my unit normals in these directions, so they each have a magnitude of 1, and they point in the direction of the x, y, and z vectors. Okay. The next operation that we might want to do with vectors is the addition of two vectors. This one is fairly straightforward. So if we have a vector A plus a vector B, all we're going to do is we're going to sum up A and B component-wise. All right? So we have the x component of A plus the x component of B in the I hat direction, plus the sum of the components in the y direction of A and B in the j hat direction, and then the same thing, the z component of A plus the z component of B, and that's our magnitude in the k hat direction. Okay, keeping with vector operations, the next operation that we might encounter is multiplying a vector with a scalar. Again, this one is fairly straightforward, hopefully, but if we have some scalar lowercase a multiplied with our vector capital A, essentially we just multiply this scalar through to each of the components of A. So we end up with our scalar A times the x component of our vector A times I hat plus our scalar A times the component in the y direction of our vector A, j hat, plus our scalar A times the z component of our vector A in the k hat direction. Pretty straightforward. All right, we get a little more complicated when we talk about multiplication of a vector with itself. All right, so when we multiply two vectors with each other, there's two different flavors of what we can do, what we can end up with that we're going to care about in this class. All right, so vector multiplication. The first one we're going to talk about is the scalar product. Or you might be more familiar with hearing the term dot product. All right, I like the naming convention scalar product because it tells you what you're going to get at the end of this operation. So we're going to start with two vectors. We are going to combine them in such a way that we end up with a scalar. hence scalar product. All right, so if we have a scalar A, and we are going to do a scalar multiplication or a dot product, right? This dot will appear between our vectors, and what we are going to do is we are going to multiply together the components of each A and B, and then we're going to sum them together. So we will have the x component of A times the B component of A plus the y component of A times the B component of the y component of B plus the z component of A times the z component of B, and we're summing these all together. So you notice I don't have any I hats, j hats, or k hats in here. They are all being taken away through this multiplication and summing procedure. The next version of this that we can have is a cross product. All right, the cross product is going to take two vectors and give us back another vector. All right, this is denoted as A cross B, so pretty literal with the notation there. And the way that we're going to do this is with a determinant setup. So I have my I hat, j hat, k hat directions at the top of this determinant, and then I'm going to write my components of my A vector across the second row here, AX, AY, AZ, followed by each of the components of our second vector, B, so we have BX, BY, BZ, and note here that the order is important. All right, so if A appears first in our cross product, it's going to be in this middle row, and then the second one is going to be in the bottom row. So our order matters here. Okay, and then now that we have this set up, we're going to just carry out a determinant of this. All right, so our first step is we are going to consider this I hat direction, and then we're going to do the submatrix determinant. So basically we cross out the rest of the row and the column that I hat is in, and then we do the determinant of this little matrix that's left over. So we have AY times BZ minus AZ times BY, right? And then we're going to repeat that process for J and K. If you remember, this J hat one, though, is a minus, so we're subtracting this one. And now our submatrix includes the AX, BX and the AZ, BZ. So we have AX, BZ minus AZ, BX. And then last but not least, we're going to add in the K hat direction, and we're going to use our determinant on this submatrix. So we have AX, BY minus AY, BX. All right, and so this is the mechanics of how we do both a dot product or a scalar product and a cross product. One thing that I want to stop and talk about here for these two vector multiplications is kind of the physical representation of what these operations imply. All right, and so it turns out that the dot product is related to the angle between our two vectors. So in this case, it's related to the angle between A and B. All right? So I'm going to draw this as a picture. So suppose we have our vector A and we have our vector B down here. In between them is some angle theta. And it turns out that A dotted with B is equal to the magnitude of A times the magnitude of B times the cosine of this angle between them. All right, so that's interesting and useful. And then similarly, our cross product is going to give us some interesting physical properties compared to the vectors A and B that we start with. And essentially what we get is the following. So this one I need to draw in a more 3D manner. So if we have our vectors A and B, if you imagine kind of on a horizontal plane here, our cross product is going to be perpendicular, and actually I've drawn this wrong. So you may recall that the cross product is going to go along with what we often call the right-hand rule. So I will show you that right here in a second. So if we have A and B, we're going to use our right-hand rule and sweep our fingers from A to B, and our cross product vector is going to point in that direction. So this is A cross B. It's going to be perpendicular to both of these two. And here's our angle theta again. And if I duplicate A at the end of B and do the same thing and duplicate B connected to my A vector here, you see I have a parallelogram. All right, and it turns out that A cross B is related to the area that is described by this parallelogram contained by A and B. All right, for the cross product, there's a few other properties that are useful to know. You can, of course, always work this out yourself as soon as you know this definition. But they are that A cross B is equal to the negative of B cross A. All right, so if you remember when I first drew this as A and B, that was wrong because that vector would point in the opposite direction, right? Okay. And we can do the same thing for cross products with our unit normal vectors. So, for example, we have I hat cross j hat is equal to k hat. All right. We also have that j hat cross k hat is equal to I hat, and k hat cross I hat is equal to j hat. All right. Okay, I've already mentioned this before for vectors that we can write a vector, let's call it v now, as vx I hat plus vy j hat plus vz k hat. And what this is essentially a decomposition of this vector into my coordinate system I hat, j hat, k hat. You can, of course, decompose a vector into any coordinate system that you so choose. And oftentimes in fluid mechanics and other engineering applications, we'd rather decompose our vector relative to a surface. All right, and so if we say that we have a surface here, and we have some vector like so, we would like to decompose it into a coordinate system that is perpendicular and tangent to our surface. All right, so traditionally the tangent to the surface vector is going to be called t hat, and the normal vector is going to be called n hat, like so. And so we essentially would like to write this as a decomposition into the normal component of v, n hat, plus the tangential component vt, t hat. All right, here the subscripts denote the component in the normal direction, and the tangent direction. Okay? And so essentially, what we are going to do is we are going to project this vector into these two directions. So you can imagine having a flashlight pointing down, and we will end up with a shadow like so. This is going to be our VT component. That's our flashlight. And then if we shine our flashlight in the other direction, like so, then we're going to cast a shadow here. And this is our VN component. Okay? We can use our dot product to figure out what Vn and Vt are. So Vn is just the total vector V dotted with the n hat unit normal. And then similarly, Vt is our total vector V dotted with the t hat unit normal. Okay? All right, so that's all I want to talk to you about in regards to vectors for this course. The next thing that we'd like to make you aware of is the notion of fields. All right? Fields are any quantity. They can be vectors, they can be scalars, they can be higher dimensionality than even that. So this is any quantity, scalar, vector, etc., that is defined over space. All right, so for example, I like to think about if you were monitoring temperature in a room. At every discrete location in the space of a room, there is a temperature that you could give it. You could put a little thermometer in each little spot of the room, and you could record a temperature. And so that means that temperature could be a field. So if that were the case, so this is temperature, our temperature, which I'm going to give the variable t, would be a function of x, y, z, the three spatial coordinates in our room, as well as time. All right, and you can think about this similarly with any other quantity of interest. So let's say that it's windy in our room, or even if it's not. We can define velocity of the air in our room as well. And each of these is a scalar as well. So we can have velocity, and our velocity vector then is also a function of x, y, z, and t. And so this is a vector field, but we also have scalar fields embedded in here, right? So each of the components of our velocity is also a field. All right, so we have our x component is going to depend on x, y, z, and t, I hat. Our y component depends on x, y, z, and t, j hat. And our z component is going to depend on x, y, z, and t, k hat. All right, so we have the total vector field. This is a field. And then embedded in here, we have three scalar fields. All right, so each of these scalar component quantities are fields because they depend on all three spatial directions as well as time. Okay, so this concludes the end of our summary of math tools that you'll need for this course. And now we're going to move into kind of the guts of this class and what it means to be a fluid. And so I will just pose you with a question to think about. What is a fluid? All right. And when we think about what it means to be a fluid, typically it's something that flows. You might be thinking to yourself, well, a fluid is a liquid or a gas. And then if you're thinking really hard, you might also include plasmas, which is true. We won't be talking about that in this class, but it is indeed a fluid. You might also think to yourself, well, I remember a fluid is anything that takes the shape of its container. And if you said any of these things, you would be correct. It also might be comfortable to kind of contrast with what is a solid, because a fluid is in many ways different than a solid, right? So we might say that fluids flow and solids deform or bend. Okay. Now let's talk about that a little bit more. All right, so what do we mean by flow? Because we've compared it and contrasted it with what solids do, which is they deform or they bend, right? So what do we mean by flow? What we mean is that this is also a deformation, but it's a deformation that deforms continuously under the application of a shear stress. And it actually doesn't matter how small the shear stress actually is, the fluid is going to still deform continuously, even if it's itty bitty. All right? This is quite different from what solids do, right? You can apply a shear stress to a solid that's small enough that it's not doing anything. It's not going to budge. It's doing nothing. It's just sitting there, right? And what this means, or another way of writing this, is that fluids cannot sustain a shear stress at rest. Okay? So let's kind of, I will take a little foyer into solid mechanics for just a brief moment to make a connection here. You may be familiar with seeing a plot of stress versus strain, right, in solid mechanics or mechanics of materials, for example. And for a solid material, this plot is generally going to follow a linear line, and then it kind of falls off. All right? What's happening here is this is our point of yield. All right, and then this slope here is E, or the modulus of elasticity. The fluid's analogy to modulus of elasticity is viscosity. So the fluid analogy is viscosity. And viscosity is essentially a measure of a tendency of a fluid to deform, okay, or to move. We're going to talk about that in a lot more detail in a little bit, but I just wanted to make that connection here. All right. And then next, what we're going to talk about is the governing equations, the conservation laws that govern fluid mechanics. Okay, so it should come as no surprise to you that since fluids exist in our physical limitations in this universe, they are going to be governed by the same conservation laws as everything else. All right, so fluids are governed by conservation laws. All right, and so these are your standard conservation laws that I'm sure you've seen in a number of other classes at this point. First one being conservation of mass. All right, mass can be neither created nor destroyed. Sometimes this is referred to as the continuity equation. They are also governed by conservation of momentum. There's two flavors of this equation, both linear and angular momentum. In this introductory course, we're going to focus just on the linear momentum one. If you stick around and see me in intermediate fluids, we'll talk about angular momentum. And then we also have conservation of energy. All right, so this is when our fluid is changing temperature, for example. And this follows the first law of thermodynamics, of course. And then last but not least, we have the second law of thermodynamics as our final conservation law. Which states that change in entropy is always going to be greater than or equal to 0. All right. Another way of thinking of the second law of thermodynamics is that essentially heat will never flow spontaneously from cold to hot. All right, things always go from hot to cold, unless there's some other driving factor. All right, in this class, we are not necessarily going to use all 4 of these conservation equations for every problem. I just want you to be aware that these are the laws that all fluids must follow and all matter. Okay? Okay. Beyond this, fluids have 2 kind of methods of considering systems that involve fluids, and they are the following. So we have 2 methods of analysis. We have control volume analysis, or system analysis. Okay, an example of a control volume analysis is to say that we have a nozzle, for example. So this could be on the end of a hose. All right, and we have some inlet flow condition and some outlet. All right, and what we're going to do is we're going to say, okay, let's define this space inside of our nozzle, and we're going to call this our control volume, and we're going to only analyze what is happening inside of this control volume. This will always be denoted CV. Just a little note on notation, for volume, I will use a V with a little slash through it so that it's never confusing that it's maybe velocity, okay? Just keep that note or in mind. All right, so this is our example of a control volume. A system would be, for example, a piston cylinder. All right, so we've got our piston, we have our cylinder, and then we have, for example, a gas inside of here. All right, so our system is going to tell us about the gross or global behavior. All right, so we're going to be looking at like work out of this cylinder. So this system is going to tell us about gross or or global behavior. Okay, so these are our two primary methods of analyzing fluids. There's also two ways that we can describe fluids. And the first one is the Lagrangian method. In the Lagrangian method, we are going to follow individual particles or packets of fluid in a flow, and we're going to monitor how they move through space. All right, one analogy that I like to use to kind of illustrate how a Lagrangian approach works is if you were to imagine vehicles on a highway, right? So if you wanted to track vehicles on a highway using the Lagrangian approach, you would be essentially using some of the strategies that autonomous vehicles use, right? So you'd have a camera that is identifying individual vehicles and keeping track of their location and velocity throughout the domain, okay? So we're going to track individual particles. In the Lagrangian approach. The other approach is called the Eulerian approach. All right, so if you go back to our highway example, in an Eulerian approach, instead of tracking these individual vehicles that are driving down the road, now we can imagine that we are taking a step back and we're like one of those traffic cameras sitting on a pole at the edge of the freeway, and we are watching the flow of cars move past us. So our perspective is fixed in space, and we're watching as the flow goes past us. All right? So here we're watching things flow past from a specific point. Okay, so for a fluid, if you think about this, taking a Lagrangian approach is really only going to be practical for a very, very limited number of cases. All right, you'd have to have a very organized flow to be able to track individual particles of the flow and what they're doing. As soon as you have something that's getting a little chaotic, this is going to go way out the window in terms of practicality. So typically, an Eulerian approach is what we're going to use in fluid mechanics. We are going to position ourselves in some stationary point in space, and we are going to watch things flow past us. Another thing that we want to talk about before we really dive into the nuts and bolts of fluid mechanics is dimensions. All right, dimensions are, of course, important in all areas of engineering. And essentially what we do in fluids and elsewhere is we are going to basically account for quantities of interest or variables that we care about in terms of primary dimensions. So all of our quantities are described in terms of primary dimensions. These primary dimensions are length, and when I'm doing dimensional analysis, I will always call this L in a bracket. The SI unit for this is meters. The second one is time, which is a bracketed lowercase t. The SI in English units for this is seconds. Our third unit is mass, and this will be denoted with a bracketed uppercase M. The SI unit for this is kilograms. And then the fourth one that we need is temperature. And this is a bracketed uppercase T, so you can see the differentiation between temperature and time. Temperature has an uppercase T, time has a lowercase t. And the SI unit for this, of course, is Kelvin. All right, and so what the big idea with these primary dimensions is that any other unit can be broken down and defined based on these four primary dimensions. Okay, so acceleration, we're using length and time. Density, we're using mass and length. And so on and so forth. Okay, one thing that's really, really important, and I find this useful across the board in engineering, but in fluids in particular, is dimensional consistency. So if you have an equation that looks like A plus B equals C, in order for this operation to make any sense at all, A, B, and C all have to have the exact same units, right? You can't add a length to mass. What would that even mean, right? And so I find that when you're starting to get into the depths of some more complicated fluid mechanics problems, if something seems amiss once you've got to the end of the problem, checking that your dimensions are consistent is a great way to figure out if you have made a mistake, where it might be. So you might find that I've calculated C, and I expected to have units of acceleration, but all of a sudden I have length squared over time squared. All right, and so you might find out that you've made a mistake with integration. Okay. All right. In this next video, we're going to talk about uncertainty analysis for experimental data. This is going to be really useful to you when you are doing lab reports and to compute uncertainty for the quantities that you've measured, and then subsequent calculations that you've done using those measurements. Okay, so experimental uncertainty. Okay, errors are always going to be present in experiments. When experiments are done and measurements are made. And they fall into two categories. That is fixed or systemic errors, and there's also random errors. All right, this first type is always the same for every measurement. So this is always the same. And it's a type of error that can be fixed by, for example, recalibrating your equipment. All right. And by fixed, I should say reduced. Because, of course, we always have errors. There's no getting rid of errors. You can reduce them, all right, but you cannot actually eliminate them. Random errors are ones that are not the same for each measurement. And these cannot be removed or reduced. Okay. So in order to estimate the error, we're going to use 3 steps. And the reason that we want to estimate our error is if we're taking a measurement, that measurement kind of doesn't have a lot of meaning unless we have a sense of how wrong it might be. What are the bounds of what that measurement might actually represent in reality? All right, so the first thing that we're going to do is we're going to estimate the uncertainty level for each measurement. All right. The second thing that we're going to do is we are going to state the confidence level on each measurement. All right. And essentially what we're going to do is we are going to say that let's say we've measured the height of something or the length of something. We're going to say it's 2 inches. All right, so we're using a ruler and plus or minus 1/64 of an inch. All right, the reason this is 64th is our confidence level is always going to be 1/2 the smallest like measurement tick on our ruler, for example. So smallest tick is 1/32 of an inch. So we just divide that value by 2. If you are using something that's digital and it reports out to the 0.01, then you are going to do your confidence level is going to be plus or minus 0.005, right? We're going to just take this and divide by 2. Okay? Next, we're going to analyze the propagation of error through calculation. And this is the tricky bit, all right? So step 2, up to step 2 is probably pretty comfortable with us, for most of us. We're pretty used to kind of knowing what the relative confidence level is for things that we're measuring directly. But of course, we're going to use those measured quantities in calculations to find something else that we can't measure directly. And so that error is going to propagate through the calculation. And so we need a way to take our measured quantities along with their error and send it through the calculation and figure out what happens to these uncertainties as they go through the calculation. Okay, so what we are going to do is a quick little example. So we are going to do a barometer reading. So if we observe the height of mercury in a barometer column to be a barometer reading, so we have H is equal to 752.6 millimeters of mercury. So Hg is just the atomic symbol for mercury. The smallest scale is 0.1 millimeters. So we want to know, what would you estimate the measurement error to be? I'm going to estimate measurement error. So we have that H is 752.6 plus or minus half of our smallest scale. So we've got 0.05 millimeters. All right? So this is our measurement error. And then we want to know our relative uncertainty. All right, our relative uncertainty is going to be given the symbol U. The uncertainty relative to the barometer height, H, is what we're after, so we want U with a subscript H. And what that is just our plus or minus measurement error, so we have 0.05 millimeters divided by our actual measurement. So we have 752.6 millimeters. So our relative uncertainty, you'll notice we have millimeters divided by millimeters. It's unitless, right? You can think of it as a percentage. And what this works out to be is 6.64 times 10 to the minus 5. Or in other words, 0.007% error. Okay? Okay, great. So I want you to keep in mind that our relative uncertainty, it has no units. We're going to denote it like this. So it's going to be U for uncertainty, and then the subscript is going to be the relative uncertainty to that variable. All right. And next, I am going to show you the expression that we're going to be using to look at what happens for propagation of error through calculation. And then we'll do an example that will hopefully solidify how you can use that expression in your own experiments. Okay, so like I mentioned, we need a tool to help us figure out how uncertainty in our measurements is going to propagate through a calculation. So let's suppose that we have a quantity R, and we want to find the relative uncertainty for R. All right, so our relative uncertainty always is denoted with U, and then we're going to put a subscript R because we want to find the relative uncertainty for R. All right, also suppose that we've calculated R using a function. R is equal to some function which is going to depend on measured quantities, x1, x2, x3, and it can use as many quantities as we want. So these are all measured quantities. And since they're measured quantities, they come with relative uncertainties of their own. So we're going to call these U1, U2, U3, and so on and so forth. Okay? Okay, so we have our expression, we have a function that we're using to calculate R. It depends on these things that we've measured in the lab, and we already know the uncertainties of these things that we've measured in the lab. Okay? So we need to figure out what is UR given all of this. All right, and so what we're going to do is we are going to use the following expression. And this expression, I've kept this general. It works for anything. You can put whatever f of x's are from your experiment, plug it into this formula, and it will work for anything that you can imagine. Okay, so the relative uncertainty of R is equal to plus or minus quantity x1, so this is our measurement 1, relative to R, partial f partial x1, uncertainty of 1, squared, plus, and we're going to do this, we're going to change out the x1s and the u1s for all the variables that we have in here, up until the very last one, which I'm going to call n. And then this whole quantity is to the square root. Okay? So essentially what we're going to do is we are going to, this is a measured quantity, x1, r1, xn, r, we know u1, and we know all the way up to un. All right, for this, partial f partial x1 all the way up to partial f partial x1, we are going to calculate this derivative. And then once we've calculated the derivative, we're going to then substitute all the mean values in the resulting equation. So we're going to compute the value using measured quantities. Okay? So I'm going to keep this equation right here, and we're going to do an example. Okay, so let's suppose that we have a golf ball. All right, we have measured its mass to be 1.62 plus or minus 0.01 ounces, and a diameter of 1.68 inches. All right, and we want to determine the precision of the measurement of the diameter of the ball so that it has an uncertainty in the density of plus or minus 1%. So we want uncertainty of density to be plus or minus 0.01, right? This is 1%. So we want to find UD, right? Okay, in our equations, in this equation, when we do this, this is the value that we will use for M. This is the value that we will use for UM. This is U rho, of course, and this is what we're going to use for D, 1.68, and then we want to find UD. Okay, the other piece that we're missing here is what is this function that we're missing, right? So we're talking about density. Density is equal to mass over volume. This is a golf ball, it's spherical, right? So our volume is 4/3 pi d over 2 cubed. All right, which we can kind of clean this up a little bit as 6 times the mass over pi d cubed. All right, so this is our function. This is our function that depends on mass, and it depends on d, the diameter. All right, so to relate everything back to our kind of general form here, R is density, right? And our x1 is m, and d is our x2. Right? We have two variables in this equation. All right, and so I am going to write this out for u rho. So our u rho is equal to plus or minus x1, which is our mass, divided by our density, right? And then I want to take the derivative with respect to x1, which is mass, of our equation, 6m over pi d cubed, right? And then times the uncertainty of 1, which is our variable m. This quantity is squared, and then we're going to do the same thing to parameter 2, which is diameter. All right, so we have diameter divided by rho, the derivative with respect to the diameter of our equation, so 6m over pi d cubed times the uncertainty of the diameter squared, and this whole thing is to the 1/2. Okay? Okay, so let's go through here and carry out our derivatives. So we have u rho is equal to plus or minus m over rho. Partial m of this expression is just 6 over pi d cubed times um squared. Plus, we have d over rho, and the derivative with respect to d of this term is minus 18 m over pi d to the 4th ud squared, and then this whole quantity is to the 1/2. Okay, we've done our derivatives, that's great. There's a few things that we might notice in here that we can simplify. So you'll notice in this first term, m divided by pi d cubed shows up, which is just our definition of rho. All right, so we end up with a rho divided by rho, and so they cancel. All right, so our first term then here ends up as plus or minus quantity of 6 squared. That's nice and tidy. Oh, I'm sorry. The 6 does not stay in there. 6 is part of density. There we go. So we have squared plus, here we have minus 3 times this diameter cancels, and then we end up with diameter cubed down here. So we have another density over density, which cancels. So this term right here is minus 3 times density. So we have minus 3 times ud squared, all to the 1/2. All right, and now what I'm going to do is I'm going to square both sides of this equation. So I have, I'm going to do this over here. So I have u rho squared is equal to squared plus 9 ud squared. All right, and we want to solve this thing for ud. So we have ud is equal to u rho squared minus squared divided by 9, and then the square root of this whole thing. All right, we want u rho to be 0.01, right? We know um is 0.01, actually. This is 0.01 divided by 1.62, right? and we just plug that in. All right, so we're going to have square root of u rho, which is 0.01 squared, minus 0.01 divided by 1.62 squared. That whole quantity divided by 9, and then we're going to take the square root of that. All right, and so this is how we find the relative uncertainty of D, such that this holds. Okay, so just to walk you back through this whole process, essentially what we're going to do is we are going to write down our quantities that we've measured along with calculating our relative uncertainty. So remember always to take your plus or minus quantity and divide by the nominal amount. So we've got our UM is 0.01 divided by 1.62. And then once we have all of that, we want to write down our equation for our calculated quantity of interest. So here we had density, that we want the equation in terms of our mass and our volume. All right, and then we can fill in our uncertainty of the calculated quantity, which is density in this case, using this formula. All right, and then after that, it's just algebra and differentiation. All right, so hopefully this puts you in a good position to deal with uncertainty in your labs with your measured